Hi there everyone, I'm Nick Sharp, and as part of SGP 2020, I'm excited to present our work on a Laplacian for non-manifold triangle meshes, and point clouds as well, as it turns out. So today we're interested in the discrete Laplacian, which discretizes the Laplace-Beltrami operator delta. This takes the form of a V by V matrix, where V is the number of vertices in a triangle mesh, and gets applied to scalar values defined at vertices. The discrete Laplacian is an extremely common ingredient in geometry processing algorithms for things like shape deformation, parameterization, shape descriptors, and so on and so forth. In this work, we'll develop a new algorithm which takes as input any triangle mesh, which might be non-manifold, non-orientable, or have boundary, and outputs a high-quality Laplace matrix. We're really excited about this because it's one of the rare cases where we can just wave our hands and make a whole bunch of useful algorithms work better. The Laplace matrix we generate is a plain old V by V matrix, and it can simply be dropped in as a replacement for the ordinary cotangent Laplacian, improving the robustness and performance of many classical algorithms. A little more precisely, our contributions are to build a good Laplacian for any triangle mesh, which might be non-orientable, non-manifold, or have boundary. And this Laplacian will have non-negative edge weights, even in the presence of boundary, and generally be more accurate than cotangent Laplacian. We also describe a simple intrinsic mollification scheme, which handles degenerate elements. And we show how the same construction can be used to get a point cloud Laplacian with similar properties. A little more formally, what we're doing here is extending the application of intrinsic Delaunay triangulations to non-manifold geometry for the first time. The key idea that makes our method work is that we sacrifice vertex manifoldness for edge manifoldness by building what we call the tufted cover. But before we get too deep into the details, a little context. This advancement is a piece of a larger effort in robust geometry processing, where we've observed that ideal meshes and formulating algorithms on ideal meshes often leads to systems, to algorithms, and to methods which don't work so well on real data. In particular, you'll notice that our ideal mesh here has a regular sampling of vertices, has equilateral triangles, whereas, for instance, CAD meshes or meshes from a 3D scanning system might have an irregular sampling of vertices and lots of skinny triangles. And algorithms formulated on this ideal mesh might crash and burn when you try to run them on real data. So we're searching for techniques which yield reasonable results across a very, very broad range of possible inputs and don't impose these kinds of restrictions. There are a lot of things that can potentially be wrong with a mesh. Most simply, your mesh might encode the wrong geometry, so it could have holes in it or spurious features. And today we're actually not going to talk about this too much more. Moving forward, there's always an assumption that the mesh you have somehow corresponds to a surface you care about. However, you still might be worried about, for instance, problems with floating point, where you care not so much just about inaccurate solutions, but also about structural problems, like getting out all nans after running your algorithm. Even if you could compute directly with real numbers instead of in floating point, you'd still have to be concerned about low-quality elements, like skinny triangles with very obtuse or very acute angles. These lead to high approximation error and poor numerical conditioning. Particularly relevant to this work are problems with mesh connectivity, for instance, non-manifold vertices or non-manifold edges. These might disagree with your formulation for a problem and very pragmatically just cause your code to crash or prevent you from using certain techniques. And in particular, once we start talking about non-manifold connectivity, you might ask, does a non-manifold Laplacian even make sense? Because classically, the Laplacian is defined in local coordinates on a surface. The good news is Laplacians really are plenty meaningful on non-manifold domains, and you can see this in a lot of ways. One way is to think about a Laplacian as a deviation from some average value. Or you can imagine just taking the variation of surface area on a non-manifold mesh. More tangibly, you could imagine taking some plates of sheet metal and welding them together in a non-manifold configuration and watching how heat diffuses along this object. Along these lines, we performed a simple experiment where we took this non-manifold shape and performed a harmonic interpolation problem in it using our Laplacian, and then similarly slightly thickened the shape, built a tetrahedral mesh, and performed the same harmonic interpolation problem. You can see that the results are basically identical, which should start to give you some intuition for how this non-manifold Laplacian behaves. So let's talk a little bit more precisely about how our method works. So as a reminder, we're going to take as input any triangle mesh without restrictions on connectivity, and output a high-quality V by V Laplace matrix. And the way our method works is that we're going to build what we call the tufted cover of this input domain, and then perform intrinsic Delaunay edge flips on the tufted cover to build our Laplacian. This tufted cover is really the new idea because it's what allows us to handle arbitrary connectivity and do intrinsic Delaunay edge flips in the context of non-manifold meshes for the first time. The net effect of this is that we're able to robustify existing algorithms. So here's a whole bunch of examples, such as harmonic interpolation, differential surface editing, and geodesic approximation. And in all of these cases, using the plain cotangent Laplacian gives you basically nonsense as an answer, whereas just dropping in our improved Laplacian gives dramatically better results. Some alternative strategies you might consider here would be perhaps just to remesh, to find some other mesh with better elements. The downside to this is that there's no such thing as a perfect mesh. As soon as you start remeshing, you have to deal with a trade-off between the number of elements, the quality, how well you approximate the underlying geometry, and the quality of those elements. And ultimately, it's always going to be a trade-off. A different strategy is to go beyond linear elements and design some custom higher-order basis functions. This is really well grounded in finite element theory, but the downside is that you generally have to go back and adapt your algorithms to use these higher-order basis functions. I should also mention that these techniques can be dramatically more expensive than what we're proposing here. Rather than taking minutes or hours, you can generally build our Laplacian in just a few milliseconds, and it costs basically nothing more than just building the standard cotangent Laplacian. So really what we're proposing to do is extremely efficient. In case you're not already familiar with it, the nearly ubiquitous construction for the Laplacian on triangle meshes is called the cotangent Laplacian. So this is a sparse symmetric matrix where for any pair of vertices in our mesh, which are connected by some edge, we get a weight in the matrix, which is given by the cotangent of the opposite angle in any triangle in which this edge appears. And you can derive this via finite elements with discrete exterior calculus, even in the context of electrical networks and so on and so forth. And I'd be remiss if I didn't mention that this is a weak Laplacian, so it gives integrated values, which means you need a mass matrix if you want to, for instance, go solve a Poisson system. Now, the cotangent Laplacian can already be applied to non-manifold domains, but there's a really, really big downside to the cotangent Laplacian. And that downside is that the cotangent Laplacian, in the presence of obtuse triangles, can have negative weights. That is to say that these cotangent weights are negative along some edge. And this generally degrades your solution, and furthermore causes your Laplacian to not have the maximum principle. So the maximum principle says that functions which have LU equals 0 have no interior local extrema, or basically that the value at any node is going to be a convex combination of the adjacent nodes. And we really want our solutions to have this maximum principle. We really want positive edge weights. We'll say that if a mesh has all positive edge weights, or all non-negative weights at least, that it's Delaunay, and meshes which are Delaunay have this maximum principle. Now, the good news is that there's a fairly straightforward way to fix this and to make sure that our Laplacian always has a maximum principle. But before we go into that, we're going to have to take a brief aside to talk about non-manifold meshes. So basically, manifoldness just means that in a local region, the mesh looks like the plane. But you might have local regions of your mesh which don't look like the plane, like for instance this non-manifold vertex in an hourglass configuration, or non-manifold edge, which has 3 faces incident on it. Sometimes non-manifold meshes arise just to a tiny small feature in some larger mesh which is otherwise manifold. For instance, the foot of this 3D scan has just a few non-manifold edges down at the bottom. Or maybe more interestingly, some shapes we're interested in are just outright non-manifold. For instance, this shows up physically in soap films when they take minimal surface configurations. And you also might see this in simulation. For instance, if you're doing a fluid simulation with 3 interacting liquids and you extract the interface between these liquids, in general it's going to be a non-manifold interface. So going back to the Delaunay property and trying to get a Laplace operator with these positive edge weights, The key tool to get there is going to be intrinsic triangulations. And the basic idea of intrinsic triangulations is to forget your vertex positions and use only edge lengths. So normally we might represent a mesh via its connectivity and a position associated with each vertex, but instead we'll represent a mesh by connectivity and a length associated with each edge. This works out because you can directly evaluate many quantities directly from edge lengths because the three side lengths of a triangle completely define its shape. Quantities which depend only on edge lengths are what we call intrinsic quantities, and you guessed it, the Laplacian turns out to be intrinsic. So the really great thing about working in this intrinsic setting is that we can perform intrinsic edge flips. In particular, given two triangles which are adjacent at some edge, we can swap the diagonal to be the opposite diagonal within the diamond, as you see here. And to do this computationally, we just need to update the mesh connectivity and compute new edge lengths, LMJ. And really what we're doing here is we're logically constructing bent triangles that lay out along the surface, or really we're constructing a better set of basis functions for the exact same geometry. And this is important because we now have the freedom to perform these edge flips and improve our basis functions and thus get a better Laplace operator. In particular, the algorithm is really simple. While any edge is not Delaunay, if it has a negative cotangent weight, you flip it. And this is guaranteed to terminate with an intrinsic Delaunay mesh. Here's one example on a mechanical part, where the black wireframe gives the initial mesh and the colored triangles are the resulting intrinsic Delaunay triangulation. Remember that our representation here is super simple. It's just ordinary mesh connectivity and a length associated with each edge. You don't have to think about the particular geometry of how these triangles sit across the surface. So this is great, and beyond giving us positive edge weights, these intrinsic Delaunay triangulations just generally improve element quality. We know that they maximize the minimum angle, which reduces condition numbers, and also that they discourage obtuse angles, which improves gradient approximation. As you see on the bottom here, we get a much more natural set of basis functions on a surface. Generally, this also leads to a more accurate discretization of, for instance, Dirichlet energy. So this is amazing and it's great, but it has a big problem because we can't flip non-manifold edges. And this is something that's really, I think, limited some of the applicability of these intrinsic Delaunay triangulations in the past because you have a very strong restriction on the connectivity. Our big contribution is to resolve this restriction, and the way we do it is really quite simple in the end, which is that we construct a particular cover of the surface. So if our input is some possibly non-manifold triangle mesh, we construct what we call the tufted cover of the surface, and then build the intrinsic Delaunay triangulation on that tufted cover. Then the Laplacian of this intrinsic Delaunay triangulation of the tufted cover is our tufted Laplacian. And our namesake here is tufted upholstery because we feel that this cover looks a bit like the buttons and fabric you see on tufted upholstery, where the vertices are acting as the buttons. One note here is that I'll draw these, the tufted cover with these curved triangles, but in reality we're still geometrically computing with ordinary flat triangles. This is just a visualization trick. So how does this tufted cover work more precisely? Well, to construct it, we'll take each face in the input and create two copies of it, which we logically think of as front and back copies. And then we walk around the original edges of our mesh and glue together these front and back copies of each face along the shared edge. So here we have front and back copies of a face, and then we walk around this edge gluing front to back, front to back, front to back at the shared side along this edge. And of course we repeat this gluing procedure for every edge in the original mesh. Looking at this here, we have a simple non-manifold mesh, which has just one non-manifold edge with three faces instant on it. To build the tufted cover, we split each face into two, so you get a front and back copy, and then glue them together along their sides at the shared edge. This results in a new set of edges, and most importantly, what's happened is that our non-manifold edge has now become three manifold edges. Since all the edges are manifold, we can perform intrinsic Delaunay edge flips and get a high-quality Laplacian. So there are some really strong guarantees that come with this tufted cover. In particular, it can be constructed for any triangle mesh without concerns for nonmanifoldness, orientability, or boundary. The tufted cover is always edge manifold, it's always closed, it's also always orientable. But in particular, being closed in edge manifold means that we can always flip the edges to make it intrinsic Delaunay, to make sure all these cotangent weights are positive. We've played a funny game here because although our construction resolved non-manifold edges, it actually creates non-manifold vertices basically everywhere. But this is totally fine because non-manifold vertices don't affect the Laplace operator. And the outcome here is that we've generated a V by V Laplace matrix, which is a drop-in replacement for cotangent Laplace. This is really effective and allows us to immediately improve the accuracy of existing algorithms. I mentioned that we're going to be able to handle even numerical floating point issues as well, and we do that with a very simple strategy. Numerically, you can run into trouble with an intrinsic representation if your edge lengths fail to satisfy the triangle inequality. And typically what will happen is your edge lengths might just barely fail to satisfy the triangle inequality in floating point. So the simple fix is that we just add a tiny epsilon to every intrinsic edge length. In particular, we'll choose this epsilon to make sure that the triangle inequality is satisfied with some small buffer in every face. And you might say, this is so simple, why are you even doing this? But this is great because it's simple. If you worked with vertex positions, there's no equivalent operation, because if you tried to move a vertex to make one face less degenerate, you might make another face more degenerate. But with the intrinsic representation, we have this really simple operation, just add epsilon to your edge lengths, which gives some very pragmatic robustness to floating point concerns. So let's look at a few applications and experiments making use of our tufted Laplacian. First, we quite simply just validated this on some data sets. So on two large data sets, which include thousands of non-manifold and numerically degenerate meshes, we're able to generate an intrinsic Delaunay Laplacian, which has a maximum principal on every single mesh. This Laplacian also has some really interesting consequences, even just for in planar domains with manifold meshes. Because since we've guaranteed that all edge weights are positive in our triangulation, in our tufted triangulation, this gives a very strong guarantee about bounded interpolation. So in particular, here, if I pin down values at 0 and 1 at two vertices of this simple planar triangle mesh, and then harmonically interpolate using cotangent Laplace, we get these crazy values much greater than 1 all along the top of the mesh. And the same thing happens with classic IDT. The reason for this is that the offending edge is at the boundary, and you can't flip boundary edges with normal intrinsic Delaunay triangulations. However, our tufted intrinsic Delaunay triangulation can flip every edge in the mesh, and thus really has all positive edge weights, and thus you get a very strong guarantee that the output of any interpolation from pinned values will always be bounded within the range of your input values. We can use our Laplacian to compute minimal surfaces, and here we get a lot of robustness to poor quality triangles. And defining minimal surfaces in terms of an intrinsic Laplacian also avoids some funny artifacts you might otherwise have in the solution, like local extrema. We can use our Laplacian to improve geodesic distance algorithms. For instance, here, taking a method for computing approximate geodesic distance and running it naively on this low-quality triangle mesh yields essentially nonsense, but just dropping in our improved cotangent weights immediately greatly improves the solution. We can also do this with differential surface head ending, where you use a numerical scheme involving a Laplacian to compute a deformation of a shape. Doing this naively with cotangent Laplace yields basically numerical noise, but swapping in our Laplacian yields a much more reasonable output. And the story continues for things like spectral methods, and you could do this for shape matching, parameterization problems, and generally across the board, you'll see that using this Laplacian improves the performance of existing algorithms. So I promised that we'll also be able to build a point cloud Laplacian using our method, and it's going to turn out to have a lot of the same guarantees. In particular, at each point, independently at each point, we'll gather a small number of neighbors, compute a normal, and then project these neighbors into the tangent plane. We then compute a planar Delaunay triangulation in this tangent plane and take just the triangles incident on the center vertex. Taking the union of all of these local triangulations, then gives us this crazy mesh, which has lots of repeated faces. It's non-manifold all over the place. It has self-intersections. But just the same, we can build our tufted Laplacian and get out a high-quality Laplace operator for the point cloud. This is great because there's no finicky numerical parameters to tune, you get good sparsity properties, and you still get a guarantee of a maximum principal. Comparing this to a few past point cloud Laplacians, the Belkin Laplacian has great theoretical convergence properties, but in practice, tuning numerical parameters means that you end up getting underflow in the solution. Here we're just computing a Green's function from a point in a scanned point cloud. Computing this Green's function with the Laplacian of Clarence et al. Is much better, but it doesn't have a maximum principal, so you get negative values in a Green's function, whereas our tufted Laplacian gives exactly the expected solution. You can use this also to adapt algorithms, higher level algorithms to point clouds. For instance, here we perform spectral conformal parameterization as well as building a logarithmic map. Looking forward, our method's able to generate a high quality Laplacian with a maximum principal for any triangle mesh without any restrictions on connectivity, and it's a drop-in V by V replacement for cotan Laplace. We also show how it's used to generate a point cloud Laplacian. Some things we'd like to continue investigating include a better understanding of the finite element implications of this construction, as well as whether it makes sense to build other operators beyond the Laplacian on our tufted cover. And finally, we'd like to investigate intrinsic refinement using this tufted cover, and this might perhaps lead to a scheme for refinement of point clouds. So if you're interested in implementing this yourself, we actually describe a simple data structure in the paper, which allows you to just track one additional matrix, which is an edge-gluing map, and makes the scheme surprisingly easy to implement. But if you don't want to implement it, we've already done it for you, and there's a code base here, which I'll link below, which builds the mesh and point cloud Laplacian and exports the matrices in a standard format. Coming soon, this will be released as a Python package as well. So with that, I'll wrap up, and thank you, and please don't hesitate to reach out if you have any further questions or want to chat more about this algorithm or anything else. Thanks.